So now we will talk about surface integrals. So surface integrals. A surface integral allows to evaluate a vector function f over a given surface S, different to line integrals. Surface integrals allows to, instead of evaluating an integral of a vector function over a given curve, we are now evaluating this vector function over a surface. So these integrals are defined as follows. It's the double integral over the surface of the vector function f and its dot product with the normal vector and the differential of area. We know that this normal vector from previous videos is a normal vector from the given surface S. However, there's another way of writing this integral. We can also describe it as follows. The double integral over a region R, that's actually a surface, of the vector function f evaluated at R, U, V, and its dot product with a normal vector that depends on U and V, du, dv. So in here what we are saying is that we are transforming a integral that is evaluated over an xj, say, plane or space to a new space that is a uv plane that allows us to make a better or easier evaluation of the integral. So the only thing that we will need to do is to transform the given surface in the xyz plane to a new representation depending on the u and v plane, uv plane. So we already know that the normal vector is defined as the cross product of the partial derivative of the parametric representation of the surface via u times the partial derivative with respect of v. And the normal unitary vector is given as follows. But we can also understand or assume that f is a vector function with three components, f1, f2, and f3, and also n will be another vector with three components, n1, n2, and n3. Thus, we can also make another representation of this surface integral as this one. F1 times n1 plus f2 times n2 plus f3 times n3, and all that multiplied by dv. And also, we can say that the unitary normal vector is equivalent to giving these three coordinates that correspond to the angle that the given normal vector is forming with the x, y, z coordinates, or planes, I would say. So if we had something like a normal vector here, we'll have the angle with respect of y, the angle with respect of x, and the angle with respect of z, and the angle with respect of x. So that way we will have these other three angles, and we can have a new representation of the surface integral as follows. So we have the integral of the surface of f1 cosine of alpha plus f2 cosine of beta plus f3 cosine of gamma, and all that multiplied by the derivative of area. And finally, we can also make another representation of the surface integral when we say that the cosine of alpha multiplied by the derivative of the area is equal to the derivative of y times the derivative of z. Cosine of b in respect of the derivative of area is z dx, and cosine of gamma derivative of area is equal to dx dy. And thus we can get yet another representation of the surface integral that will be something like this. Is equal to f1 dj dz, dy dz, sorry, plus f2 dz dx plus f3 dx dy. So there we have one representation, two representations, three, and four representations. Then we have four ways of evaluating the surface integral. So now let's make this simple example. We have the parametric representation of the surface and the given vector function to be evaluated on this surface. So we will need f evaluated at the parametric representation of the surface, that will be equal to minus u squared comma v squared comma 0. And we also will need the normal vector of the surface that depends on u and v, that is equal to ru cross product with rv. So first we will need to get ru, that will be equal to 1, 0, 3, and rv, that will be equal to 0, 1, minus 2. So this cross product will be equal to k 1, 0, 3, 0, 1, minus 2. And this will be equal to 3i and minus so plus 2k and plus k. If I'm right, that I believe I am, well, now this is minus, and yeah, now this is alright. So the normal vector will be equal to minus 3, 2, and 1. So now we can evaluate the integral. We know that v goes from minus 2 to 2, and u goes from 0 and 1.5 of the given vector function multiplied by the given normal vector du dv, and we will have something like this: minus 2, 2, 0, 1.5, 3u squared plus 2v squared dv, that would be equal to minus 2, 2, u cubic from 0 to 1.5 dv plus minus 2 to 2 of 2uv squared dv from, so here 0, 1.5, there it is. So we have minus 2 to 2 of 1.5 cubic dv plus minus 2 to 2 of 2 times 1.5 v squared dv equals to 1.5 to the third of v minus 2 to 2 plus 2 times 1.5 v cubic over 3 from minus 2 to 2. This will be equal to 1.5 cubic times 2 plus 2 times 1.5 v cubic over 3. Sorry, this is not v cubic. This will be now 2 cubic over 3 minus 1.5 squared minus 2 plus 2 times 1.5 minus 2 cubic over 3. And let's make the math. 1.5 cubic plus 2 plus 2 times 1.5 times 2 cubic over 3. Okay, this will equal to 59 quarters. 1.5 cubic times minus 2 plus 2 times 1.5 times minus 2 cubic over 3 plus 59 quarters. This will be equal to 29.5. And there you have it. Finally, we have another type of surface integral. We have noticed surface integral is defined as follows. That is always dependent of the normal vector of the given surface. So this normal vector will indicate us that this integral is dependent of the orientation, because this normal vector will give us the orientation of the surface. However, we can also evaluate these surface integrals without regard of the orientation given by these other kind of integrals, where we have g of r dA equals to, it's the same integral but now evaluated in the UV plane. So now we see that we are no longer taking into account the orientation of the surface, and that is also seen here because we are only obtaining the absolute value of this normal vector. And another important application of this kind of integrals is that we can get the area of a surface, given that this g is now considered the density, for instance, of a surface. We get that the area of this surface is given by the double integral over the surface of the differential of area. So if we integrate this differential of area, we will get the total area of the surface. However, we can also represent this in the UV plane as follows. Considering that we know that the normal vector is defined as the cross product of the partial derivatives of u and v. So here is another way of evaluating surface integrals without regard of the orientation, and a way to obtain the area of a given surface.